Hello. Today I'm presenting work that Chaitanya and I did at a May hackathon. The talk is titled Porting a Python Markov Chain Monte Carlo Method to RAPIDS during the SDSC GPU hackathon. Like I said, this was a hackathon that we did in May. We had the good fortune of being accepted, but a little bit of background first on who I am and what the work is related to. So I am an assistant research professor at Arizona State University. I work in the Computational Research Accelerator, which is a unit adjacent to the group that maintains the supercomputer here at Arizona State University. And around this time last year, we were approached by a professor in the economics department for help with accelerating a MCMC, or Markov Chain Monte Carlo simulation, that he had written in Python to model the utility of a specific board structure, which we'll talk a little bit more in a few minutes. And I just want to say thank you again to the NVIDIA mentors that we had at the hackathon. Without the help of Drs. Oded Green, Hyun Ju, and Sarefson Kudian, we would have probably missed at least an order of magnitude in speed up that was achieved as a result of using the GPU to accelerate the Python code. So I'm going to give a little bit of background first on what Monte Carlo and what Markov chains are in order to motivate why it is important to accelerate these routines for the broader community. So Monte Carlo simulation is in essence randomly evaluating an integral. So for instance, on the right-hand side here, you can see an animation where these different colored circles are appearing. Basically, you can think of dropping seeds into a square domain where a quarter circle is drawn. And if you count the number of little seeds that are on the inside of the circle and compute the ratio of that to the total number of seeds that have been dropped and multiply that number by 4, congratulations, you've estimated pi. And this is an example of a Monte Carlo method, and a really nice one. You can see in the bottom part of this animation a convergence plot. So I'm plotting the relative error there on a log-log scale, and that straight line slope that's there has a slope of -1/2 on the log-log scale, indicating that in order to get an extra digit of pi, I need 100 times more seeds, right? So over here, the estimate of pi is roughly 3. 100 times more estimates later, it's nearly 3.1. 100 times later, nearly 3.14, and so on. So Monte Carlo methods are highly parallelizable, but they are slow to converge. So you need to run a lot of samples to achieve the appropriate convergence. Whereas Markov chains, well, we see these all the time, perhaps without realizing it. For instance, meteorologists have utilized Markov chains to tell us what the probability of the weather of the day is going to be like. So for decades, if not centuries, meteorologists have observed days being sunny and then partly cloudy and then rainy and so on. And from that, they can develop a model that is frequentist-based, on the data that they have, understanding that if a day is sunny, there's a 75% chance that the next day might be sunny. And you can then construct a table of those probabilities of state transitions. And congratulations, you've developed a Markov matrix or transition matrix that, if you compute the leading eigenvector of, tells you the observed equilibrium distribution. Right, so there are important properties in Markov chains that I don't necessarily have time to get into here, but the equilibrium distribution here tells you, for instance, that you can expect roughly 71% of all days to be sunny. So how do these two converge? Well, not all integrals or probabilistic problems can be uniformly sampled, which is typically how you employ a Monte Carlo method. The Markov Chain Monte Carlo method, in essence, prescribes a specific kernel, and they were created to estimate high-dimensional problems. So in a nutshell, when you're running MCMC, you're running a Monte Carlo simulation that takes a lot of samples in order to converge to a certain level of tolerance that trends towards a pre-described Markov chain equilibrium. And the convergence is similar to a Monte Carlo method in that it's order 1/n to the 1/2 power. So you need 100 times more samples to get an extra digit of convergence, where this tau is essentially a characteristic time of how long it takes for the autocorrelation to disappear from the Markov chain. Okay, so this is an important aspect that makes it difficult to parallelize these now modern techniques for estimating high dimensional integrals. The Monte Carlo method, you can simply distribute out the work to as many workers as are available. But with Monte Carlo methods, you have to take steps where you redistribute the work in order to prevent too much autocorrelation between the workers and divergence away from the Markov chain equilibrium. So essentially, you're running Markov chain or Monte Carlo simulations in stages that can be parallelized, but the work has to be harvested in a serial way. Okay, so what did we do? So the professor came to us with this work, and the utility that he wanted to measure was for the staggered board. In essence, a way to organize some type of committee, for instance, board members on a corporation or even faculty committees, in a way that prevents rapid change and encourages higher risk projects so that higher up leadership can't just come in and remove everyone. And his original code, it was taking 110 hours, so 4 days and 14 hours to do 10,000 iterations. And this was not a sufficient level of convergence, and he had to run 4 different parameterizations of this integral. So it was taking nearly 3 weeks to run, a base level simulation. And to get an extra digit of convergence, which was necessary, it was going to take over 15 months for just one of these cases. So what we did first was look at the code and understand there were some simple things here that could be changed, such as variable caching. So that led to a 2x speed up. Or more sophisticatedly, a lot of these MCMC methods employ a lot of element-wise multiplication on higher order tensors, like 3rd order, 4th order tensors. So upon realizing that, we put into global memory what was actually static and used einsum to do the heavy lifting. And that led to a 20x speed up. So without the GPU, we were able to speed up the code by about a factor of 20. And most of the routine, or most of the computation as the result of a profile, was spending time evaluating a Gaussian, just plugging in values of mu and sigma, the mean and standard deviation, and returning the result, as well as actually doing that einsum, which are both 2 operations that are, or 2 methods that are very fast on the GPU. And we knew that we could use RAPIDS to potentially take our NumPy code and accelerate it. So we were fortunately accepted into the hackathon, and we had the expertise of our mentors. And, on the first day, we were able to get roughly a factor of 2 speed up by very carefully on an A100 with 80 gigs of RAM, replacing all NumPy calls with CuPy calls and slight modifications to the initialization. And the profile completely changed. So at the top there, you can see that the total time of einsum was about 140 seconds for a benchmark case out of 444 seconds. Einsum no longer took any time on the GPU. Instead, what started to end up taking all the time was a memory allocator, this RMM CuPy allocator. And without the help of our mentors, we would not have come up with this elegant solution. But it turns out there's an RMM module that's a part of RAPIDS. And RMM in this case stands for RAPIDS Memory Manager. And this allows you to allocate how much memory needs to be on the GPU. So with really 2 lines of code, in line 11 here plus line 8 is all we needed, but we used the more verbose version on lines 8, 10, 12 through 17 to more specifically say how much memory we thought we needed on the system. And the allocation led immediately to significant speed up. So what did that look like? Well, the original code took 110 hours. There was a 28x speed up by considering the variable caching and the einsum representation. The GPU just natively got us a factor of 2 speed up. But then with this RMM manager, we were able to get an additional 20x speed up for a total of 540 times compared to the original code. And because 4 of these need to run simultaneously, and on the supercomputer here, we do have multiple A100s, they can all be run simultaneously compared to the original workstation, resulting in a 2,000 times speed up. So 1,000,000 iterations instead of 10,000 would have taken 15 months originally for just one case, but now 1,000,000 iterations takes 20 hours. This is significantly worth it, not just for the researcher, but also for anyone on our systems that uses MCMC, which is a very broad community. This is one research group in the economics department. Most other research groups in our economics departments are using Markov Chain Monte Carlo to estimate their high-dimensional integrals and to understand the utility of their hypotheses. In fact, I've started working with another researcher that was implementing something in Python this last week from the economics department that's using MCMC to evaluate the utility of solar panels versus traditional electric utility, or EV cars, electric cars versus gas-powered cars. And, looking at her code, it's once again something that should benefit quite a bit from the plug-in ability of RAPIDS. And then outside of the economics community, STEM in general, especially in physics, loves to use MCMC to evaluate high-dimensional integrals. So what all of this tells me is that Python, with the use of RAPIDS, has become a state-of-the-art solution for researchers evaluating high-dimensional integrals. And without using a low-level language that perhaps a graduate student that's coming in doing research doesn't know how well to use, like C or Fortran or C++ or these days Rust, now that graduate student can maybe learn how to put together some Python code with RAPIDS and achieve state-of-the-art performance. Okay, so outside of the broader impact, the hackathon, I have to say, was incredible. Okay, so it's like 5 days of serious commitment, but the level of expertise is, it's just amazing that it's a free event. Let's put it that way. The level of commitment from the mentors and how they guide the teams in learning how to implement the different techniques is really extraordinary. And we have started to encourage other faculty and labs here at ASU to submit their own projects to the hackathons and hope to work with NVIDIA and the OpenACC community in the future to maybe host a statewide hackathon here in Arizona. But back to the project itself, I just want to point out a couple quick technical details before I conclude. Python does everything in 64-bit. It's the default type. I'm talking about convergence in like the 4th or 5th digit. 64-bit is overkill. And yeah, there are technical details that I can get into this application, but I'm just going to come to my conclusion slide to say one other thing about the hackathon. So a lot of these slides were actually written for the hackathon itself, because another nice thing that is taught at the hackathon is Scrum. Every day you have to put together a presentation and share with your peers that are also at the hackathon what you've done that day, what your plan is for tomorrow, how it's affected your goals. So there are really nice software engineering lessons that are also built into these hackathons. So without further ado, I'm going to say, please attend a hackathon if you have a project that's relevant. Well, all right, then let's go ahead and close it there. Thank you again for your attention.